I'm about to start a battle in the comments, but I want to tell you my solution to the most highly debated problem in probability theory. Sunday night, Sleeping Beauty, with her consent, is put to sleep and has her memory wiped. Then a fair coin is flipped. If the coin comes up heads, Sleeping Beauty will be awoken Monday and the experiment will end. If the coin comes up tails, Sleeping Beauty will still be woken up Monday, but then will be put back to sleep with her memory wiped, woken up again on Tuesday, then the experiment will end. The kicker is, every time Sleeping Beauty is woken up, she's given the details of the experiment and asked the question, what do you believe the probability is the coin came up heads? A simple question with a simple answer. Except it's not. On one hand, it's a fair coin. Before the experiment, if you asked Sleeping Beauty what the probability of a heads would be, she'd say a half. And even though when she's woken up, she's told the details of the experiment, she doesn't know what day it is, and she doesn't know how many times she's been woken up, and so she doesn't really have a reason to change her viewpoint. On the other hand, we have an entire probability theory which we should probably be able to apply here. Sleeping Beauty is rational, and upon waking, she begins to reason to herself. Say the coin landed tails. If the coin landed tails, Beauty would be awoken on Monday and Tuesday. Having her memory wiped would make those events indistinguishable to her. So we should conclude, given that the coin came up tails, the probability that it's Monday should equal the probability that it's Tuesday. After using the definition for conditional probability, we can conclude that the probability the coin landed tails and it's Monday is the same probability as the coin landing tails and it's Tuesday. Beauty continues to rationalize, saying, well, what if it was Monday? Regardless of the coin flip, the day Monday will happen in the experiment. Given that this is a fair coin, the probability that it came up heads should be the same probability that it came up tails as long as we're only considering Monday. Again, by the definition of conditional probability, we can say that the probability of landing tails and being Monday is the same as the probability of landing heads and being Monday. We had the probability of the coin landing tails and Monday from our last thinking exercise, so let's use the transitive property to link these three things together. These three events all have equal probabilities, and they're the only events that can happen in this experiment. Since they're all the possibilities, adding up their probabilities must sum to 1 or 100%, and since they're all equal, the probability of each of them happening is 1/3. Only one of those scenarios had the coin landing heads, and so the probability of the coin landing heads was 1/3. So which is it? Is the probability of heads 1/2 or 1/3? And honestly, I have a hard time arguing with the math here. In this situation, it really looks like it should be 1/3. And I think that's the point. In this situation, there are variants on this problem carrying the experiment out over thousands of days, and the longer you make the experiment, the smaller the probability of a coin getting heads. It seems this question isn't really asking what's the probability of a coin landing heads. We can all agree that that's 1/2 if we're thinking of a future coin flip. This question is more like asking what's the probability of getting heads and it's Monday in this experiment you're in right now? Or in other words, which of the three scenarios does Sleeping Beauty believe herself to be in? Answering that question is a lot different from asking the question, what if I flip this coin? At the time of recording this video, I believe the probability of heads is 1/3 according to the situation of the Sleeping Beauty problem.
Let's play a game, you and me. The rules are simple. We each make one of two choices. Either to work with the other player, that's called cooperating, or work against the other player, that's called defecting. We each make one of those two choices, and neither of us knows what the other player chooses. That gives us 4 different possible outcomes with 4 different payouts. If we both choose to cooperate, we both get 3 points. Well done. If we both choose to defect, we both get 1 point. Here's the interesting part. If one of us defects while the other cooperates, the defector gets 5 points while the cooperator gets 0. Now everyone knows the rules, and everyone knows the rules. You want to play? I have my choice. Do you have yours? Ready? Sorry, I chose to defect. Meaning if you chose to cooperate with me, not only is our trust a little broken, but I get 5 points while you get nothing. If you chose to defect also, well, that's not so great for either of us, we each get 1 point. If you want to play again, just rewind the video. I promise I'll make the same move since it's the best strategy. It's always better for me to defect regardless of your choice. In fact, that's the best strategy for both players. But how can defecting be the best move for both players? Each of us ending up with 1 point is clearly worse than both of us cooperating and each ending up with 3 points. Let's look at this game rationally, meaning you're playing to win. Let's say you know I'm going to choose to cooperate. What would your best move be? Knowing I'm cooperating, your payoffs are between 3 if you also cooperate, or 5 if you defect. So what's the better move? Defecting. You'll simply earn more points. Now say you know I'm going to choose to defect. What would your best move be now? Knowing I'm defecting, your payoffs are between 0 if you cooperate and 1 if you defect. So what's the better move in this case? Defecting. Again, you'll simply earn more points. No matter what your opponent chooses, it's better to defect. This is a dominant strategy, and in this case, a Nash equilibrium. That's when neither player can benefit by changing from their current strategy. And this is so frustrating since it's a setting where two rational individuals, both acting in their own interests, don't cooperate, even though it appears it would be in their best interest to do so. It makes you want to lean to the other player and whisper, "Hey, just cooperate and so will I. We'll both be better off that way than if we stick to this so-called best strategy." I had a really interesting experience playing this game in college when I took a mathematical game theory course. Our professor really liked The Prisoner's Dilemma, so much so that one day we were all paired up and asked to play against each other for extra credit. We had the two usual choices, cooperate or defect, and the payout structure was something like this. If both players cooperated, each received a bonus point in the class. If you both defect, neither of you gets the bonus point. Finally, if one defects while the other cooperates, the defector gets 2 bonus points while the cooperator loses a point in the class. Everyone knew all the rules. Everyone knew all the rules. We had been studying game theory all semester, and everyone knew what the best possible strategy was. What do you think most people chose? Almost everyone, including myself, chose to cooperate, knowing full well we would have been better off individually not doing so. Now, maybe this wasn't a perfect experiment. 1 or 2 points probably wouldn't have affected anyone's overall grade, so maybe we didn't care enough to play perfectly. Also, when we played, each pair had to go up to the front of the room and pretty much everyone could see how things went down, so we could see who all the jerks were. Despite this, I still find it interesting that even knowing how we should play the game, the best strategy, many of us chose not to do so.
Maybe you've seen some of the simple arguments for why 0.9 repeating equals 1. 1/3 is certainly 0.3 repeating, and if you multiply both sides by 3, you get what we want. Maybe you've even taken Calc 2 and seen that 0.9 repeating can be represented as a geometric series, a convergent geometric series, and you just use the formula a over 1 minus r to sum the geometric series, and you get 1. But even after numerous proofs like this, you just can't accept that 0 out front of the decimal point and think that these numbers are in fact the same. Let's do a formal proof so you have no choice but to accept this result. For now, let's just agree 0.9 repeating is less than or equal to 1. I doubt that you think 0.9 repeating is greater than 1. Let's try to also agree that 0.9 repeating is a real number. Maybe we'll talk about hyperreal numbers a different day. If you can agree 0.9 repeating is a real number, then we're all set. If 0.9 repeating is a real number, then it has to play by the rules of the real number system. And the real numbers are continuous. There are no breaks or gaps in the real number line. A mathematician might call the real numbers dense. That means between any two distinct real numbers, we can find another real number between them. An easy way of doing that is taking the average of the two distinct numbers. So if 0.9 repeating and 1 are two distinct real numbers, they're not equal, well, there has to be some value we can fit between them. Let's just call it x, and now we have this inequality. Let's try to figure out what x should be. To do that, let me introduce a new notation, 0.9 sub n. This represents the sequence of 9s with n9 repeating. Here n can be any natural number. So for example, 0.9 sub 1 would be 0.9, 0.9 sub 2 would be 0.99, 0.9 sub 5 would be 0.59s, and so on forever. Since 0.9 repeating has an infinite number of 9s, we can fit this sequence into our inequality. Something to note about 0.9 sub n is that if we add 1 over 10 to the n to it, it equals 1 for all n. For example, let n equal 3. That would be 0.999 plus 1 over 1,000. 1 over 1,000 is 0.001, and those sum to 1. So here comes the magic. Let's look at both sides of our inequality. 0.9 sub n less than or equal to x means the same thing as negative 0.9 sub n is greater than or equal to negative x. X less than or equal to 1 means the same thing as 0 is less than or equal to 1 minus x. And from our equation, 1 over 10 to the n equals 1 minus 0.9 sub n. Let's string these three ideas together. 0 is less than or equal to 1 minus x, but minus x is less than or equal to 0.9 sub n. And 1 minus 0.9 sub n equals 1 over 10 to the n. What's the consequence of this? That quantity, 1 minus x, is non-negative. It's greater than or equal to 0. And it's less than 1 over 10 to the n for any natural number n. The larger n we pick, the smaller 1 over 10 to the n becomes. So it won't take you too long to figure out that 1 minus x has to be pretty small. In fact, it has to be 0 if we're being less than 1 over 10 to the n for any n. This is essentially the same thing as the Archimedean property. Well, if 1 minus x has to be 0, that means x has to be 1. What was x in the first place? X was that thing between 0.9 repeating and 1. And if the only number between 0.9 repeating and 1 is 1, it must be that those numbers are not different. They have to be the same number.
Let's play a game. Pick a numbered door, 1, 2, or 3. One of these doors is a winner. There's a big prize behind it if you select it. However, behind the other two doors is nothing. You don't know which door has the prize behind it, but I do. For argument's sake, let's say you select door number 1, hoping for the prize. Before I let you know if you've won or not, I'm going to show you what would happen if you selected door number 2. Turns out door number 2 was a loser. There wasn't anything behind it. That doesn't matter though, because you chose door number 1. Now I'll pose the question. Would you like to switch doors? Do you want to trade door number 1 for door number 3? On the surface, it doesn't really seem like it should matter. When you first selected your door, there was only a 1/3 chance you selected correct. And now that you know one of the doors that didn't have the prize, there's still only a 50-50 shot between which door has the prize, right? I mean, you still don't know where the prize is. There doesn't seem to be any intuitive reason why switching your choice at this point would benefit you at all. The obvious answer to the question, should you switch doors, is it doesn't matter. However, that line of reasoning is very flawed. And I'll prove to you that in this situation, it's always better to switch your choice after a wrong door has been revealed. How can that possibly be? Here's one solution to the famous Monty Hall problem. I'll admit it's not entirely satisfying to everyone, nonetheless it completely proves that switching doors is always in your best interest to do so. Let's look at each possible scenario beginning at the door you select, number 1. There are 3 possible places for the prize: behind door number 1, behind door number 2, or behind door number 3. If the prize is behind door number 1, there's nothing behind door numbers 2 or 3. If the prize is behind door number 2, nothing is behind 1 or 3. And finally, if the prize is behind door number 3, nothing is behind 1 or 2. The way the game works is that I know where the prize is, and I will always reveal to you one of the options you didn't choose that also didn't have the prize. So if you choose door number 1 when the prize is behind door number 1, and also choose to switch doors, you'll receive nothing. But if you choose door number 1 when the prize was not behind door number 1, that is either of the two other scenarios, choosing to switch doors will give you the prize. When we look at every possible situation, the act of switching gives you the prize in 2 out of 3 of those situations. Another way of saying that is your probability of winning is 2/3, 66% when you switch, not 50% like it might appear on the surface. And this might make no intuitive sense. How could switching doors ever give you an additional chance of winning, even when you never knew where the prize was in the first place? The subtlety lies in the simple fact that we were given more information after the start of the game. Me, the host, didn't open a losing door at random. Knowing that there were 2 losers, learning where one of them is, gives us additional information and updates our probabilities. Here's a more extreme example to drive this point home. Place the numbers 1 to 1000 on pieces of paper inside a hat. You pick one number out of the hat without looking, and you win a prize if you drew the number 999. Before you look at the number, I'm going to show you every other number you didn't draw except for one of them. And none of the numbers I reveal is 999. In other words, you either drew the winning number, 999, or the number I didn't reveal is 999. Would you like to trade the number you drew from the hat with the number I didn't reveal? And in this situation, do your chances of winning really feel like 50-50? Or does it seem way more likely you drew the wrong number and 999 was left in the hat? I think in this case, your intuition would be to switch. It seems much more likely you didn't draw the winning number and would almost certainly be better by switching. Of course, this is in fact the case and the best strategy for the same reasons as the Monty Hall problem. This is just on a larger scale. You're running around a track. 2 laps to be precise. The first lap, take it as slow as you like. The question is, how fast do you have to run during the second lap so that your total overall average speed is equal to twice the speed of your first lap? Admittedly, when I first heard this question, I thought, no problem. Let's just average the 2 speeds. I'll call them v1 and v2 for velocity of the first lap and velocity of the second lap. We just add these and divide by 2 to take their average, and this should equal twice v1, twice the speed of the first lap. A little bit of algebraic manipulation, v1 plus v2 should be 4v1, and v2 should be 3v1. Or in other words, we should run our second lap 3 times faster than the first lap to satisfy our conditions. Except this thinking is wrong. Performing the calculations this way assumes that the velocities, the speeds, are equally weighted. If we're computing our total average speed of 2 laps, and the second lap goes faster than the first, well, the second lap is going to take less time than the first. So our average speed isn't v1 plus v2 over 2, it's the total distance of 2 laps divided by the total time for 2 laps. So we should really think of it like this. Speed is distance divided by time. Let's let d be the distance around the track. Let's let t1 be the time it takes to complete the first lap, and let's let t2 be the time it takes to complete the second lap. So what's really our average speed? Speed is distance divided by time. How far did we travel in 2 laps? Well, each lap was a distance of d, so we traveled 2d. How long did it take us to travel 2d? Well, the first lap was t1, the second lap was t2, and so our total time was t1 plus t2. What's this supposed to equal? Twice the speed of the first lap. What's the speed of the first lap? d over t1. And now we have an interesting thing happening algebraically. We can cancel 2d on both sides, meaning that the distance around the track doesn't matter. That's nice. And we can try solving for t2. If we try to shuffle things around to solve for this relationship, we're going to see that t1 canceling on both sides as well and get that t2 is 0. Or in other words, to satisfy the constraint of this question, we would need to complete the second lap in 0 seconds. We need to run infinitely fast to answer this question. Let's play a game where you'll win some money. Sound good? We'll start with $1 and flip a coin. If it's tails, you get the dollar. Congrats. If it's heads, we'll double the amount to $2 and flip again. If the coin lands tails, you get it all, $2. If it's heads again, double the pot again. And we can do this forever. Keep flipping until you get tails. That's when you get to take the money. For every heads in a row, I'll double the stake. Here's the question. How much would you pay to play this game? Keep in mind, there's a 1/2 chance you walk away with $1 from the start. A 1/4 chance you walk away with $2, and this would continue so on forever. Have your answer? My guess is that you'd probably be willing to pay a few dollars to play. Maybe 10 or 15 if you're feeling generous. What does math say you should be willing to pay to play this game? We can calculate it using what's known as expected value. That's what the game is worth to play. We find this by multiplying all the different possible outcomes by their respective probabilities and adding everything up. The first possible outcome is winning $1. That happens if your first flip is tails, which happens with probability 1/2. The second possible outcome is winning double, $2, by flipping a heads, then a tails, which happens with probability 1/4. You would win $4 by flipping heads, heads, tails, probability 1/8, and maybe you can see the pattern. We double the winnings and half the probability each time. And theoretically, this game could go on forever. Simplifying our expression, we can see we're adding up infinitely many 1/2s. 1/2 added to itself infinitely many times would be infinity. So what does the math say you should pay to play this game? Though I doubt anyone would, math says you should offer up everything you have, since on average, this game will pay out an infinite amount of money. So will you do it? Probably not. And I think that the on average piece is part of the resolution to this situation. Expected value computes the weighted average of all possible events. In this case, an infinite number of them with exponentially decreasing chances of occurring. Just because the average is infinite, it doesn't mean it would be the value to an individual player. There's also a bit of human behavior wrapped into this question. Losing money is often more painful than the joy of gaining that same amount. Then there's the issue that I don't have an infinite amount of money to wager either, so maybe the whole question is bogus. It's a nice day and you're walking over to meet your friend. But before you reach your friend, you'll have to walk half the distance to your friend. And before you walk half the distance, you'll have to walk 1/4 the distance. And before you walk 1/4 the distance, you'll have to walk 1/8 the distance. Before that, 1/16 the distance. Before each mark, you'll have to walk half the distance to that mark. And this can go on forever. In other words, before you reach your friend, you'll have to complete an infinite number of tasks. How are you going to do that? And since there are an infinite number of them, there's no first task. How can you even begin your journey? As you ponder this, somehow, miraculously, you reach your friend. And although your head's in the clouds, your friend really wants to race. Now, let's be honest, you're way faster than your friend, and this isn't a great matchup. So you decide to give your friend a head start. You both start running the race, knowing you'll quickly catch up to your friend. thing is, by the time you've covered the distance between you and your friend will have ran a little more. And once you make up the new distance between you and your friend will have ran a little more. Once you cover that distance, your friend will have run a little more again, and so on forever, and you'll never win the race. Despite realizing this, you pass your friend and win. And although your friend is a little discouraged, they still would like to hang out with you and pass a ball around. And as you throw the ball back and forth, you get a nagging feeling. Although the ball you throw is clearly in motion, at any instant in time, it's not. If we were able to take a snapshot of any instant in time, we would see the ball is not moving from anywhere and not going to anywhere. At every single instant of time, no motion is occurring. Yet time is entirely composed of instants. And if everything is motionless at every instant, how can motion happen? These are Zeno's paradoxes, and are still somewhat debated in modern times. How do you think we can resolve them? This being a math channel, maybe I'm a little biased, but I believe the hidden mathematics resolve these paradoxes. In our first problem, we had to walk half the distance to our friend, but before that we had to walk a fourth of the distance. Before that, an eighth of the distance, and so on. We can write this list as a sequence of numbers. Each number represents a task, a distance we have to walk, in order to complete our journey. Our journey can be represented by adding up all of the tasks, summing these numbers. Problem is, there are an infinite number of them. Fortunately, calculus comes to the rescue. This is what's known as a convergent series. There's a variety of ways to find the value of this sum, but this one happens to be a geometric series which has a very nice formula, and we can compute its value, which happens to be finite. Of course, we knew the value would be 1 just by looking at the distance we had to walk. Our one journey walking to our friend is composed of half that journey, 1/4 that journey, 1/8 that journey, and so on. There is one overall journey, so of course this sum should be 1. Admittedly, this argument might not fix every issue from each paradox, but I think this is a fairly comfortable resolution since we've shown just because an event can be broken down into an infinite number of tasks, that doesn't mean the event itself is infinite. Here are 2 envelopes, each containing money. You can have one, and it's your choice between the 2. You don't know how much money is in the envelopes, but I will tell you one envelope has twice as much money as the other. Okay, have your choice? Before you open your envelope and pocket the cash, I'll give you the option to change your mind. Do you want to switch envelopes? Does it matter? The obvious choice is, who cares if you switch envelopes? It shouldn't matter. You didn't know how much was in either envelope to begin with, so how could switching help? But trying to look at the situation mathematically makes things pretty interesting. Let's let the amount in our selected envelope be x, since we don't know it. The other envelope either contains twice as much, 2x, or if we did select the better envelope, the other envelope contains half as much, x/2. The probability x is the smaller amount is 50%, and the probability x is the larger amount is also 50%. Using these probabilities, we can calculate what's called the expected value. That is, the amount we expect to earn by switching or not. If we don't switch, the expected value is easy. We get x with 100% probability. If we do switch, there's a 50% chance we get 2x and a 50% chance we get x/2. We calculate the expected value by multiplying the probabilities by the value and adding. 1/2 times 2x plus 1/2 times x/2. Simplifying these fractions gives us 5/4 times x, or 1.25x. In other words, our expected value of switching is 25% more than keeping the envelope we originally chose, x versus 1.25x. What's going on here? How can switching be a better strategy regardless of which envelope we originally chose? Let's think of this creatively. Here's a few ways of looking at the problem that attempt to resolve this mathematical paradox. If one envelope contains an amount A and the other contains twice as much, 2A, the total amount T in both envelopes is A plus 2A or 3A. If you selected the envelope with the amount A first, you gain the amount A by swapping. You're trading A for 2A, so you've gained an additional A. If you selected the envelope with 2A first, you lose the amount A by swapping. You're trading 2A for A, so you've lost the amount A. On average, half the time you gain A, half the time you lose A. Adding these together gives us 0, the intuitive value of switching envelopes. Another solution looks at the expected value differently. If one envelope contains the amount A, the other envelope contains the amount 2A, then the expected value of the envelope you choose is 1/2 times A plus 1/2 times 2A, which is 3/2 A, 1.5A, regardless of which envelope you originally chose. This means, on average, the amount you receive is the average between the two envelopes, which makes sense. Thus, there's no contradiction here. A more philosophical resolution to this problem takes issue with how we assign probabilities. The way that the problem was presented, that we take the envelope and say that the other envelope has an undetermined value based on probabilities, isn't quite the case. The fact is, the money is locked inside the envelopes before we even start. One envelope has A and the other has 2A. Choosing an envelope, saying it has value x, and that the other envelope has 2x or x over 2, each with probability 1/2, is a bit disingenuous. It's like trying to assign probabilities to events which have already been determined. My take on the problem: these issues are arising because you stand to gain twice as much as you would lose by switching envelopes. If you have an envelope with x and the ability to switch, you stand to end up with 2x, a 100% gain, or end up with x over 2, a 50% loss, each with equal probabilities, and this is leading to these asymmetrical expected values. But you only stand to gain more money if you think of the value of the other envelope as undetermined. In my mind, once the money's in the envelopes, it's locked in. The only undetermined calculation going on here is your probability of choosing the envelope with more money, 50%. And the chances you choose the correct envelope again by switching is still 50%. What's kind of frustrating is that even though many solutions have been presented, at the time of this recording, to my understanding, no proposed solution is widely accepted. 1 minus 1 over 1 minus 1 over 1 minus 1, on and on forever. If we continue this fraction, it approaches an imaginary value. How could that possibly be? After all, this is a sequence of real numbers, and it appears to approach a complex number. Where do we get that result, and how do we make sense of it? To figure that out, let's look at the more tame continued fraction, 1 plus 1 over 1 plus 1 over 1 plus 1, and so on forever. If we start writing out the terms of this sequence, we'll see very quickly they start approaching this 1.618 number. You might know this as the golden ratio. And in fact, if we define this as a recursive sequence, notice if we called this quantity x, then 1 plus 1 over x would be the same as this definition. We could sort of fit x inside itself over and over and create this infinite fraction. This makes it very nice to simply solve for x, multiplying both sides of this equation by x, shuffling around the terms, and using the quadratic formula, we get these results. Now, since we were only working with positive numbers, let's just throw away the negative number and have 1 plus root 5 over 2. That's that 1.6 number, also known as the golden ratio. And so we've solved for what this continued fraction could be. It's a very nice representation for phi, the golden ratio. Let's try to do the same thing with the original question. Trying to solve the continued fraction 1 minus 1 over 1 minus 1 and so on leads us to an interesting result. If we define this relationship recursively, it's very similar. And just treating this like an equation with x, we can solve it in a very similar way. Multiply both sides of this equation by x, shuffle around the terms, and use the quadratic formula. Interestingly enough, in this case, our answers are complex. We get answers involving the imaginary unit I. So does that mean this repeated fraction equals one of these complex numbers? Well, not so fast. Earlier, our sequence converged. All of those iterations were approaching the golden ratio, that 1.6 number. But if we look at the iterations of this continued fraction, it's all over the place. In fact, we made a very subtle error assuming that this fraction converges at all when it doesn't. At least not if we're only considering real numbers. I want you to imagine you're in algebra class, and your teacher is going on about some silly topic, imaginary numbers. I squared is -1, and something about multiplying by I being a rotation of 90 degrees. As you're half paying attention and flipping through your textbook, you see something scribbled in the margin. Go to the old field behind the school where the supply shed is. Walk directly from the shed to the pine tree, counting your steps. Once there, turn 90 degrees to the left and walk the same number of steps away from the tree. Mark this point. Go back to the shed and walk to the willow tree, counting your steps. Turn 90 degrees to the right this time and walk the same number of steps. Mark this spot also. Treasure is buried halfway between the marked spots. Your heart begins to race. Immediately after class, you rush out to the old field only to discover there's no trace of the shed. You see the pine and willow trees, so the treasure has to be here somewhere. You feel a bit dismayed that you might have to dig a lot until inspiration strikes. Maybe you can actually use some of the stuff you learned in class. Pretend this field is the complex plane. The real axis is horizontal and the imaginary axis is vertical. And pretend the trees are at -1 and 1 on the real axis. The shed used to be somewhere in the field, thus its position would have to be at some a plus bi, where a and b are real numbers, they're just unknown. We can subtract the real and imaginary components of the shed and the trees, giving us vectors. These vectors represent not only the distance but the direction between the shed and the trees. Since you learned multiplying by I gives a counterclockwise rotation of 90 degrees about the origin, we can multiply this first value by I, rotating the point 90 degrees counterclockwise. Now this isn't quite in the position where it should be. We'll have to compensate by then subtracting by 1. Now it's in the place of our first marking. Let's do the exact same thing with the second value, except we want to multiply by -I to rotate this counterclockwise 90 degrees. Again, it's not quite in the right spot. We'll have to compensate by adding 1. Now we have the location of our two markings, and we know the treasure is halfway between them. We can find the midpoint by adding the two complex numbers and dividing by 2. After a bit of algebra, we see a and b magically canceling out. That is, the position of the shed didn't matter, and the treasure will be located at positive I in our complex plane.
7 moves. The birthday problem, or the birthday paradox, is a fascinating piece of mathematical probability theory that illustrates how bad humans are at estimating probability in statistics. Here's the question. How many people need to be in the same room such that the probability of two people having the same birthday is above 50%? Want to take a guess? Maybe you think 100, maybe a little bit more. The answer is 23. That's right, it only takes 23 people in the same room to have a greater than 50% chance that any two people have the same birthday, which is extremely counterintuitive. But all you need to do is work out the combinatorics and the probability, and there it is. I think what most people confuse this with is the probability that you yourself has the same birthday as someone else. That's much more unlikely. But the question's asking, do you share a birthday, and does anybody else in the room share a birthday? And when you think of it like that, the odds get much higher.
To solve exponential type things like I to the I, we often insert an e to the ln. We can do this because the exponential and logarithm functions are inverses. They undo each other. And the reason we do this is because of those properties of logarithms that let us drop down exponents as a coefficient. So e to the I, natural log I, is a different representation for I to the I, and something we can figure out. We just have to know how to deal with logarithms of complex values. To figure this out, let's remember that any complex number can be written in the form a plus bi. You might call this rectangular coordinates or a Cartesian system. Or we can represent it in terms of polar coordinates, drawing this triangle and using the legs of the triangle, r cos theta and r sine theta, instead of a and b. We can factor out that r, which is the hypotenuse of the triangle, and hey, look at that, there's the famous Euler's formula. Cosine theta plus I sine theta is e to the I theta. So any complex number can be represented as r e to the I theta, r being the distance from the origin, and theta being that angle measured counterclockwise from the positive x-axis. This is now very convenient to take the natural logarithm of, since again we can apply properties of logarithms, splitting up this product into a sum of logarithms. And again, we're seeing natural log and e canceling out, just going the other way. Again, those are inverse functions. They undo each other. Now we know what the natural logarithm of a complex number should be. It should be the natural logarithm of r, the distance from the origin, plus I theta, theta being that angle measured counterclockwise from the x-axis. To compute natural log of I, how far is I from the origin? Well, it's a distance of 1 from the origin, so in this case r is 1. I lives along the positive vertical axis, and the angle theta is 90 degrees or pi over 2 radians. Thus, natural log of I is natural log 1 plus I times pi over 2. Of course, natural log of 1 is 0, and we can answer our question. It's e to the I times pi over 2. By definition, I squared is negative 1, and we get I to the I is e to the minus pi over 2, a real number. There is a caveat if we think about coterminal angles. I does indeed make a 90-degree angle with the positive x-axis. Theta is pi over 2. But we could travel around the circle another 2 pi radians and end up in the same place. So theta could be pi over 2 plus 2 pi, and we get a different result. In fact, we could do this infinitely many times, either clockwise or counterclockwise, and get an infinite number of solutions. But we often restrict our discussion to a single interval, and when someone says I to the I, they usually mean this value is about a fifth. Everyone knows if you keep adding a bunch of positive numbers forever, you'll go out to infinity. Except that's not actually true in every case. Calculus students learn about sums that look like this, known as convergent series. We're adding up infinitely many positive numbers, but they actually converge to a finite value. And this is just my first example on this frustrating list of mathematical theorems that seem obvious, but are actually false. Knowing that previous fact might lead you to conclude if we have one of these so-called convergent series, an infinite list of numbers summing to a finite value, that you can rearrange the terms of that sum and end up with the same result. After all, one of the first things you learn in algebra is commutativity of addition, that the order in which you add numbers doesn't matter. Well, that's true for a finite list of numbers, but we actually have the Riemann rearrangement theorem, which says that if a sum is conditionally convergent, you can rearrange the terms to make it converge to essentially whatever you want. Since our example only converges if each term is not in absolute value, we call this conditionally convergent. And if I start rearranging the order of these terms, we can make it sum into whatever we want. We can make it converge to any number, or even diverge. You know that shapes with finite volume have to have finite surface area. I mean, that's obvious, right? Well, maybe not. This is the famous Gabriel's horn generated by the function 1 over x. It's often given to calculus students and is a great counterexample to this theorem. We can use improper integrals to show that the volume of this object is finite, yet its surface area is infinite. You can sort of intuitively justify this to yourself by taking a cylinder of clay. If you roll the clay up so it has half the diameter it did, you still have the same amount of clay, the same amount of volume. But then it would be 4 times as long and hence twice the surface area. And if you were somehow able to continue this process ad infinitum, the volume would remain constant while the surface area would grow arbitrarily large. Every single natural number can be put in the numerator of a fraction, and every single natural number can be put in the denominator of a fraction. That's a whole lot of combinations. And so clearly there are way more fractions, rational numbers, than there are natural numbers. Well, that's not actually true. What exactly do you mean more numbers in one set than the other? I think we can both agree there are an infinite number of both of them, but it sure feels like there are more fractions than there are natural numbers. A mathematician might look for a bijection between the two sets, essentially looking for a way we can pair up every single element of both sets. If every element from both sets had one partner, then there would be just as many elements in each set and they would have the same cardinality, the same size. Well, here's a very fun way to do it, laying these out in a grid. Just assign 1 to the first number, 2 to the second number, 3 to the third in this pattern going out, and you'll see that every single natural number can be assigned to a positive rational number. Thus, they are actually the same size set. And there are not more rational numbers than natural numbers. So now when I say there are just as many natural numbers as there are numbers in the interval 0 to 1, that's gotta be a true obvious statement. Except when we do the so-called Cantor diagonalization argument. These two sets have the same size, the same number of elements, if we can match up every single element pairwise. Let me try to do that. Let me create a list matching the numbers 1, 2, 3, and so on out to infinity with every single number between 0 and 1. Here's my list. Except I'm going to create a new number with the first decimal of the first number, the second decimal of the second number, the third decimal of the third number, and so on forever. This number is not on the list because it's not the first number, it's not the second number, it's not the third number, and so on. We've created a number which is in the set 0 to 1, but not on the list. This set is uncountably infinite. And in a sense, there are more numbers between 0 and 1 than there are natural numbers.
When I first came across this so-called Grandi's series, I didn't think a whole lot of it. By using our standard methods, this series clearly diverges. Just use the test for divergence, see that this limit doesn't exist, and there you go. I saw the unrigorous attempts at trying to sum this series. If you arrange parentheses like this, it looks like we're just adding up a bunch of zeros, and so this sum should be 0. But if you arrange parentheses like this, it looks like we're adding up 1 plus a bunch of zeros, and so the sum should be 1. Clearly associativity wasn't going to do the job. The next unrigorous method tries to use the distributive law. Just do 1 minus this sum and distribute. You would basically distribute the negative, and so we would end up getting 1 minus 1 plus 1 minus 1. That's just the original sum we started with. And so 1 minus the sum equals the sum? Or 1 equals twice the sum? And the sum is 1/2? Like, no way, that's totally ridiculous. Adding and subtracting a bunch of ones to get a half makes no intuitive sense, and I was about to write this off as a fluke. But as I dug deeper, this 1/2 kept showing up. There's this idea of Cesaro summation, which instead of doing a traditional sum, which is the limit of the partial sums, it takes the average of the partial sums. This summation is sort of like a less restrictive convergence, and when we apply it to our Grandi series, you get 1/2. And it turns out there are numerous methods that when applied to this series, you get 1/2. But despite all this, I still wasn't really convinced yet, until I started to look at the geometric series. The good old geometric series x to the n summed from n equals 0 to infinity. This equals 1 over 1 minus x, so long as x is between -1 and 1, not including those endpoints. If we substituted x equals -1, we get our Grandi series. But we can't substitute -1 into the formula 1 over 1 minus x. That's outside the interval of convergence. Well, it's really right on the tip of the interval of convergence. So if we can't evaluate right at x equals -1, what if we approached it? What if we did limits? If we let x approach -1, then the geometric series approaches the Grandi series, and its sum approaches 1 over 1 minus 1, or 1/2. That's pretty interesting, but we know limits as x approaches a can be different than the function evaluated at a. I was just about to give up when I stumbled across this idea that has become very popular at explaining these type of weird phenomenon. This idea of analytic continuation. That interval of convergence, -1 to 1, think of that as like a domain of this function. We want to extend that. We want to push the boundaries to include more things. A way to do that is through Taylor series. Taylor series give us great approximations for a function around a certain value. You see, the sum of x to the n is basically like a Taylor series centered at a equals 0 for the function 1 over 1 minus x. Well, let's come up with a different Taylor series centered around a different value so we can push or move that domain, that interval of convergence. To make it alternate like our Grandi series, let's just substitute in -x to get the function 1 over 1 plus x. We'll find the Taylor series for this centered at a. How do we do that? Well, we need to take derivatives of this thing until we see a pattern, basically, and then substitute x equals a. The 0th derivative is the function itself. You could take another derivative using the reciprocal rule, another derivative using the reciprocal rule, and if you don't combine anything, you start to see this alternating pattern as well as a factorial shows up. And it looks like after doing repeated derivatives, the pattern f nth derivative evaluated at a is n factorial over 1 plus a to the n plus 1. Let's just slip this into our Taylor series formula. The sum from n equals 0 to infinity of that derivative we just found times x minus a to the n over n factorial. This is pretty nice because once we substitute this in, a bunch of stuff cancels and we get this nice simplified Taylor series. What you might notice is that if we let a equals 0, you just get the good old geometric series. So the geometric series is sort of just centered at 0. But centering at 0 didn't work because of its interval of convergence. We want our interval of convergence to be around x equals 1. Why 1? Well, that's because if we substitute 1 into this, we get our Grandi series. So we should probably pick A to be something close to 1. There's many choices we could use here. Let's use 3/4. If we substitute 3/4 for A and do a ratio test to see what the interval of convergence is, we see that x equals 1 is indeed inside this interval. So we're all good. Now the fun part. This Taylor series is a geometric series, and we know how to sum it. The way we sum geometric series is a over 1 minus r. A is the first term of the series, r is that common ratio. Let's just substitute these values in. A little bit of algebraic simplification, and what do you know? We get 1 over 1 plus x, which we should. So if we substitute in x equals 1 via an analytic continuation, this equals our Grandi series, and its sum converges to 1 over 1 plus 1, or 1/2. I'm still not entirely sure that I'm convinced, but this argument is pretty compelling.
Start with an equilateral triangle. Next, divide the sides into 3 equal segments. Draw more equilateral triangles, so the middle segment of each side is the base of the equilateral triangle. Remove the base of each mini equilateral triangle, and repeat this process indefinitely. Take each side, break it up into 3 equal segments, draw an equilateral triangle on top of the middle segment, then remove that middle segment. This is what's known as the Koch snowflake, and it's one of the earliest fractals to have been described. What I love about it is that its properties are a little paradoxical. Let's look at the perimeter of this object. To find the perimeter, we'll have to describe each iteration. The first iteration would just be the base triangle itself. This would be the second iteration, the third, and so on. We'll have to know how many sides are present at each iteration in order to find the perimeter. Let's let capital N sub n denote the number of sides at iteration n. The way that this pattern works is that each side is then replaced with 4 sides. So we could say that the number of sides of the nth iteration is the same as the number of sides of the previous iteration times 4. We start with 3 sides to begin with. Every iteration, we multiply the number of sides by 4, so the number of sides of the nth iteration should be 3 times 4 to the n. What about the length of each side? Let's let capital S sub n denote the length of each side after n iterations. Now we didn't specify the length of the side of the original triangle, let's just call it little s. And since we divide the side lengths in thirds, every single iteration will divide each side length by 3. So s sub n should be s over 3 to the power of n. Now we can find the perimeter. The perimeter of this shape, I'll call it p sub n, the perimeter after n iterations, should be the number of sides times the length of the sides. That's just 3 times 4 to the n times s over 3 to the n. You could rewrite this with properties of exponents. Let's just call this 3s times 4/3 to the n. This is our perimeter after n iterations. So you might be wondering, well, what happens if we just do this process forever? What if we take the limit as n goes to infinity? After we do an infinite number of iterations, what do we expect the perimeter to approach? Well, taking this limit, the quantity 4/3 just keeps getting larger and larger. 4/3 is bigger than 1. Multiplying it by itself over and over is going to get bigger and bigger, and so the limit of the perimeter is infinity. This perimeter should be unbounded. Here's the paradoxical part. What if we look at the area of this object? Since we're talking about area, we'll have to know how many triangles there are, not just the number of sides. Let's let capital T sub n denote the number of new triangles added in the nth iteration. Well, the new number of triangles we add just depend on the previous number of sides. We start with 3 sides and we add 3 triangles. So T sub n is actually capital N minus 1. The number of triangles added is the number of sides from the previous iteration. And we already had this value. Just a quick bit of algebra, we can see that this is 3 times 4 to the n minus 1. What about the area of each triangle added? I'll call it a sub n. The thing to notice here is that each new triangle is 1/9 the area of the triangle in the previous iteration. If we start with this original equilateral triangle, again, we didn't specify the original area of the first triangle. Let's just call it A naught, A initial. Since we divide up one of the sides into 3 segments, it has 1/9 the area. Which means that the area of each new triangle added is A naught divided by 9 to the n being the nth iteration. Here's the fun part. We have a formula for the number of new triangles added, and we have a formula for the area of each new triangle added. So the total area added by each new iteration, I'll call it b sub n, should be the number of triangles added times the area added. Just multiply our two formulas together, and we can make this look a little nice with properties of exponents. That's the total new area added in each iteration. We're interested in the total area of the snowflake altogether, so we have to sum this iteration for every value of n. Let's let capital A sub n be the total area of the snowflake after n iterations. That's A naught, the original area of the triangle, plus the sum of b sub n. This is a fairly funky formula, but what's great is that we can still use it to find the limit as n goes to infinity. If we were to perform an infinite number of iterations, what would the area of this object approach? And so what we have here is an infinite series. This is something that you would probably come across in Calc 2. This series is what's known as a geometric series, and it has a very nice formula that gives us its result so long as the base in absolute value is strictly less than 1. Here the base is 4/9, so it's all good. Just plugging this into the formula, doing a little bit of algebraic number crunching, we get our answer as 5/8 times A initial, which means the area of this Koch snowflake is only 5/8 times the original area of the triangle. It's a shape whose perimeter approaches infinity, but its area approaches a finite value.